Episode 1, Automated Testing and Inversion of Control, A Rope of Sand.
I'll title it, What It's Like to Be a Teenage Clone, A Rope of Sand.
Good title, it draws the reader in without giving too much away. Wesley.
Automated tests are a spectacularly useful coding tool. Start with a thesis, bam. Unit tests are so important that they should be a first-class language construct. Let's talk about why. 1. Regressions.
We've got Decepticons at the gates, Decepticons in the air, Decepticons inside the walls, Decepticons. If we beat them with the walls, then they're still in the air. If we shoot them out of the air, then they're still at the gates. So where does that leave us? Nowhere, that's where.
We've all worked on systems where you make one small change over here, and another problem pops out over there. So you go over there and fix it, but 2 more problems pop out somewhere else. You constantly push them back, like that whack-a-mole game, and you just never finish. If the system is not orthogonal, if the pieces interact with each other more than necessary, then you'll always get that kind of distributed bug fixing. I'm using that quote out of context. It's supposed to be a point in favor of designing systems modularly, so that the bugs don't come up in the first place. The thing is, though, even in a well-designed system, code still interacts with other code. I mean, it has to. We do our best to keep the interactions to a small, well-defined minimum, but code that doesn't interact with anything at all doesn't usually do anything at all. Code in a single class, for example, interacts with other code in that same class. And yes, when you make changes in the code, you can break things. Things that other people wrote. Things that you wrote a few days ago and forgot about. Things that you wrote just now and didn't think about because you're dumb. If there are automated tests to check that everything is still working as promised, then you can catch these things before something bad happens. And now that you have the safety net of a good set of automated tests, you can change the code with impunity. 2. Documentation.
But I don't know what they are, where to find them. I don't even know what they do.
The Elements of Harmony, a reference guide.
How did you find that?
It was under E.
As much as the combination of function signature and documentation are supposed to be enough to make the intent of your code completely and perfectly clear, it doesn't often communicate the best way to use your code. Let's look at some of the documentation for Beautiful Soup. The first paragraph explains what it is. Then, immediately after, before any in-depth analysis of what's going on, live code examples of how to use the code to do some things that you might want to do with it. Python really embraces this philosophy with docstring tests. Tests right in the function's documentation that manage to both clarify how the function is used and automatically test the function in the same space. Even if unit tests aren't in the documentation, though, they still serve as live operational examples of how to use your code. Those are some of the benefits of unit testing. Now let's talk about how to do it. 1. Find a unit testing framework. A unit test framework exists for developers of every stripe. Java, C#, Python, C++, the one guy who programs in Haskell, Ada, Visual Fox Pro. The 2 features that characterize unit testing frameworks are the ability to run every unit test in your solution and see the results, and helper functions providing assertion logic. So, with your unit test framework set up, you should be in a position to write a function that tests something. Of course, you can write your unit tests any way that you please, but there's a mnemonic to help you remember how to put together a solid unit test. Arrange, where you set up the environment with the proper test conditions. Act, where you perform the action that you're testing. And assert, where you check that the environment is now in the correct state.
You know, we get a lot of complaints for not being rigorous on this show, and I think it's because the show makes it look like we only do these experiments once or twice, when in fact, we run these repetitions as many times as time and money will allow. It's not easy to get a big data set on Mythbusters.
Yeah, how many times did we do that eel skin and wallet experiment anyway?
God, like 500 times?
2. Once you have tests, run them regularly. Talk to your build guy. If you don't have a build guy, run a script to check out your codebase and run the tests periodically to let you know when somebody has checked in code that's broken a test. Do not check in code that breaks tests. Punish people who do with silly hats. 3. Only test the thing you're testing. Let's talk about the difference between unit tests and integration tests. Let's imagine that you're testing a car. You want to make sure that the car works properly, so you create a car-driving robot to sit in the front seat, drive the car around a bit, fiddle with the knobs, trigger the airbags, that sort of thing. This is an integration test, a test of many parts working together to create a complete system.
Hit all 10 Santa bowling pins, which will yank on the string. Send the skiers down. The skiers going down will yank on this magnet, which hammer will hit the stove. The stove, which has roast in it, will release its roast onto this seesaw, onto the dinosaur platform.
Now, there are lots of problems with integration tests. They're complicated and they break very easily. They don't produce a lot of information about what broke. They usually have a lot of setup and teardown steps. Any change to the program's behavior usually means a change to the tests. They take a long time to run, and they may produce inconsistent results run to run. So, while a few sanity check integration tests are useful for making sure that your system is fully operational, maintaining a suite of integration tests soon creates a maintenance nightmare. Instead, we focus on testing individual components, individual classes, in isolation. This is a unit test. But with every class having some kind of dependency, how do we isolate that class for testing? Inversion of control and dependency injection. Let's imagine that you have code that executes queries against a database, and you want to test that code. Traditionally, you might have code to include your SQL library, instantiate a connection, and make the queries. But then, how do you test this without an active SQL connection? I mean, you could set up a special test database containing data that you need to run your unit tests, and find a way to simulate special test conditions, like a failed connection or... Instead, you could just have the code request an object that implements database functionality in the constructor. That way, we can pass in the real database in the live system, and a fake database for testing when we're testing. In the live system, we still need to instantiate this code with a live database connection. But where do we do this? Anywhere we instantiate the database connection, we've made the code untestable. What if we had some functionality to create that object for us and provide it when necessary? If anybody asks for an iDatabase, use this MySQL database. This is an IOC container, or Inversion of Control container. You could build your own, of course, but dozens of implementations of this concept exist for a variety of languages. For example, Castle Windsor for C#, or Spring for Java. Spring isn't actually the IOC container, but it contains one. There are other benefits to the IOC style as well. It's a good way to build modular systems where objects can easily be replaced by others, but we're getting off topic. 4. Mocking and stubbing. Now that we're testing a class that takes an interface to a database instead of a database, all we have to do to test it is pass in an object that pretends to be a database. This is called a mock, or a stub, depending on whether or not the fake object has any behavior. And once again, while writing the class yourself isn't that hard, there are dozens of mocking libraries out there that'll do this for you with a minimum of fuss. Mock, Fake It Easy, Mocks, Mocker, RhinoMocks, Mock. And there are lots of places where mocks are very useful. You can mock out things that supply non-deterministic results. You can mock out things that have states that are a pain to reproduce. You can mock out things that are slow. And you can mock out things that don't exist yet. Now, you don't have to mock out every dependency from every class that you write. If the behavior of the dependency is reasonably simple and itself well tested, mocking may not be necessary. Definitely keep it in mind, though. 5. Pitfalls. Remember that unit tests are part of your codebase too. They have a development cost, a maintenance cost, and they don't directly produce value for your users. Going crazy with overzealous testing and mocking might produce code that's light on bugs, but expensive to produce and change. The right balance of testing to production code is something that will change from team to team and from product to product. High maintenance tests, and tests that intermittently fail on their own, are almost always more trouble than they're worth. Too much logic in your tests or mocks is a code smell. You don't want to codify implementation details into your tests. That's a mistake. If you reach the point where you feel like you might need unit tests for your unit tests, you've gone too far. Well, that's all I've got for this. Thanks for watching. Oh, and this is my first time doing this, so if you could answer some questions for me, that would be great. How was the technical content of this lecture, and what topics would you like to see more of in the future? Okay, thanks again.
Well, I'm off.
What?